5-2?
Yeah, I think I'll just kind of start 5-2, and if I have some time, I might back up into 5-1 before the day's over. But I don't know, I think I'll just do this, 5-2. Now, so the first thing is, there's this symbol. So this is a Greek letter, sigma, capital sigma, and it means summation. Maybe you should have seen it maybe in pre-calculus or somewhere in your math career. It means add some stuff up. Usually what happens then is there's like something on here that has a little index, I, and then it says we're going to add all these things up from I equals 1 to whatever. Sometimes we just stop at some abstract number n. I mean, what does this say? This says you plug in a 1 and you get x1. Okay, you're done with x1. Then you plug in a 2 and you get x2. Okay, and what do you do to these things? You add them. You put little addition symbols in, and you add these things. So who's next? X3. And then maybe plus ... Who's last? Xn. You know, maybe that n is a 10. Maybe I'm adding up 10 things. But it's just n at the moment. So it's xn. Are you guys okay? I mean, this is totally new. I mean, we haven't used this symbol in this class. And you barely used it maybe in other math classes, but it is just a summation. It's not that difficult. It's a summation symbol. You're adding something up. Here, let's try this was kind of abstract. I'm adding up a bunch of xi's from 1 to n. Here, we could add up something a little more specific. You want to add up I squared from I equals 1 to 3. This one's kind of more specific, and so now the little I is called sort of the index or the variable of this summation is I, and you go from 1 to 2 to 3. You don't stop at 1.5 or 1 3/4 or 2.7 or you just, it takes on these integer counting values 1, 2, 3 like this did. Anyway, it's easy. You plug in a 1, you get 1 squared. This is 1. You plug in a 2, you get 2 squared, which is 4. You plug in a 3, you get 3 squared, which is 9. And one more time, what is in between those things? Plus. Thank you. It's because this means summation, and so we add these things. We are adding these things. So there's a final answer here. What's the final answer? 14. 14. Cool. Hey, I think when my child turns 14, when I get a cake at Publix, I think I'll have him put this on there. It's 14, dude. There's no doubt about it. It's 14. If my child can't figure that out, then they don't get a piece of cake. It's a hard life, you know what I'm saying? You gotta earn your birthday cake. Mathematically. So you guys all right? I'm trying to introduce a summation symbol, which maybe you haven't worked with too much. And in a way, I don't know, might not work with it all that much right now. It comes up again big time in chapter 8. But it's sort of in a different context up there. All right. Well then, here's the big point here then. So this is just a little preliminary teaching you about a symbol, just a little bit here. The big point is, what I want to do is find the area under a curve. So I'm going to try this. I'm going to give you a function here. I'm making up this function. I'm going to use x squared plus 3 as a function. I'm also going to work on an interval from 0 to 2. And so I want a good looking picture of this. So here it is. Here comes a good looking picture of this. X squared plus 3 is a parabola that hits here at 3. You know, it's a parabola. It opens up like this. It also opens up over here, but paying attention to my interval there, I'm working from 0 to 2. So I'm just going to work here from 0 to 2. I'm going to stretch out this 2 here. I'm sorry, I'm sort of stretching out my picture here. That's a 1, that's a 2. You guys okay? I mean, what have I done? I'm talking about a function on an interval, and I drew a picture of it. But here's the new cool thing, and this is major calculus concept, but we build toward it without some calculus for a minute. I want the area under the curve. I want what's called the area under the curve, and this is a new trippy idea. I mean, before today, and you'll help. You're gonna help me figure this out today. But before today, I mean, can you do the area of a rectangle? Yeah, good job. I'm real proud of you. Length times width. Yeah, you're fantastic. Can you do the area of a square? Yeah, great job. Can you do the area of a trapezoid? Or, you know, if there's geometric formulas for these shapes, right? Can you do the area of a circle? Yeah, pi r squared. But can you do the area, and mine's not that crazy, but can you do the area under some crazy curve, dude? And the truth is, yes. With calculus, we can calculate this area. It's amazing. I mean, right. After today, we've moved beyond rectangles and squares, and we can do the area under curvy, beautiful, curvy, crazy shapes. We can find the exact area under a curve. Let me show you how you do it. Actually, you do it using basic geometry. I just poo-pooed rectangles. I shouldn't have done that. We use rectangles to do this. Here's what we're going to do. We're going to estimate this area at first. Then we'll figure out how to get it exactly. But first, we estimate this area, and we're going to use n equals 4 rectangles at first here. So what I'm going to do is I'm going to partition this x-axis into 4 rectangles. If you're going from 0 to 2, then if you want to cut this into 4 rectangles, well, there's 2 rectangles. Now I need to do it again. Now, by the way, if you're looking at that, you're probably saying, wait a minute, that ain't a rectangle. I called that a rectangle. I called that a rectangle. I know it doesn't look like it, does it? Well, it doesn't look like it. It's got a curvy top, right? It's not a rectangle. Right. All right. Hang on, we'll get there. Hang on, we'll get there. But actually, I want 4 of them, so I'm going to cut this in half again. Is that okay with you? Yeah. So now I have this partitioned into 4 pieces. I'm trying to get the area from 0 to 2. I've sliced it into 4 rectangles, but again, you're going to look at that and say, they ain't rectangles. They kind of look like a rectangle until you get to the top. The top is a curvy top, right? You agree with me? Kind of look like a rectangle, except the top is a curvy top. Okay, well, we're going to make it a rectangle. We're going to make it a rectangle by cutting off the top and making this nice straight top. And there's a few different ways to do this. So one way to do it is to do it with what we call a lower sum. And if I'm going to do a lower sum, then I'm going to top off my little rectangles with I'm going to use the minimum height on each for each rectangle. I could call it a rectangle. I could call it a little sub-interval. You know, I'm working on this interval from 0 to 2. You guys happy with that? I'm working on this interval from 0 to 2. But I've created 4 little sub-intervals. 0 to a half to 1. You with me on this? 4 little sub-intervals there. So let's just look at this first sub-interval. Look, let's pick the minimum value from 0 to a half. Where's the minimum height? The minimum height. 3. Right over here at 3. It occurs at this x value, 0, right? All right, and so if I top this off right there, I could have a rectangle, and I can calculate its area. You know, because I can calculate the area of a rectangle. Hey, will it be exactly right? No, there's some error involved. See that little error? Right, there's going to be some error involved. Let's move to the next rectangle. To the next rectangle, if I want to make it a rectangle, I'm going to chop off the top. I'm going to top it off, but I'm going to do what's called a lower sum. So I want to use the minimum value to top it off. What would that be? Right here? Yep. Right here. Which again, that's the minimum value. I'm going to cut off the top. I'm going to make that a rectangle, and I'm using this 1/2, this left endpoint. I'm doing what's called a lower sum, and when I start to draw these rectangles, what I'm drawing here is, I'm going to write this, I'm doing inscribed rectangles. The word inscribed means they're inscribed under the curve. If you were to inscribe a circle in this square, I'm just trying to emphasize the word inscribe here for you. If I want to inscribe a circle in a square, do you think it would be this? Of course, I kind of didn't mean to float outside a little bit there. Sorry. That's inscribed in the square. Watch this. If you want a circumscribed rectangle, circumscribed circle around the square, that would be this. Just teaching you the words circumscribed and inscribed. The circle's inscribed in the square. The circle's circumscribed around the square. You could say the square's inscribed in the circle. You could say that, I guess. Okay. So turns out these lower sums, using this minimum height, what I'm getting is inscribed rectangles. So do you believe that? You're learning a lot of new language here. That's what I'm getting. All right, listen, I want to actually do this. So I'm going to kind of build a little chart here, and I want the area of these 4 little rectangles. The first thing I need, though, I think, is I need the width. Then I'm going to need the height. Then I'm going to multiply width and height, then I'll have area. But I'm going to do this for all 4 of my rectangles. You ready? My 4 little rectangles. Now here I go. What is the width of this one? Half. A half. What about this one? Yeah, good. We cut it evenly into 4 rectangles. From 0 to 2, cut into 4 rectangles. The width is a half, right? Right. Okay, you can see it. It's labeled well. You can see it. The width of each rectangle is going to be called delta x. That's the width of the rectangle. And we just said it's a half. So for the first rectangle, it's a half. Hey, for the second rectangle, it's a half. For the third rectangle, it's a half. For the fourth rectangle, it's a half. You with me? Mm-hmm. All right? I'm doing my 4 rectangles here. Okay, now I need these heights. These heights are changing here. And these heights are y values, right? The height is a y value, and it's where it hits the function, you know? So, like this first rectangle, what's the height? 3. The height is 3. You're totally right. It's that y value, 3. Now, hold on. I got it, though, maybe by plugging in 0 into the function. I mean, this is the x value that gives you this height, right? Mm-hmm. So let's just try plugging 0 into this function. What height do you get? 3. You get 3, of course. But it's this left endpoint. You hear me? Left and right endpoint. It's this little left endpoint that gave me the inscribed height. And so I'm going to denote that like this. So this height is going to be called f of little mi, and I'm using a little m for the minimum. The minimum. I'm trying to get this minimum height for these inscribed rectangles. Okay. All right, here we go. So the first rectangle, you said you're plugging in a 0. I'm going to write that. I'm plugging in a 0, and what height do I get? 3. 3. Okay, thank you. For the second rectangle, what do I plug in? So for the second rectangle, to get that height, I need to use this x value. Good, thank you. So I'm plugging in a 1/2. the 1/2 ain't the height. The 1/2's the x value you plug into the function to get the height. You guys with me on that? Yeah. The function value is the height. The function value is the y value. All right, well now I gotta, let me move this over a little bit here. I need some room there. I gotta plug a 1/2 into the function. That's a 1/2 squared. That's 0.25 plus 3. I think it's 3.25. You can help me. You guys got calculators. But that's that height, I think. For the third rectangle, what are you going to plug in to get the height? 1. You're going to plug in a 1. For the fourth rectangle, what will you plug in to get the height? 3/2. So in this particular example, we keep plugging in this left endpoint, don't we? And we get the heights of these inscribed rectangles. Cool. Let's do it. Plug a 1 into the function. That's easy. 4. You get a height of 4. Plug a 3/2 into the function. It takes a little work. All right, thank you. 3/2 squared plus 3. You're saying that's 9/4 plus 3. That's really 2 1/4 plus the 3 is 5 1/4. Somebody said that, right? Yeah. 5.25, I think you said. Okay, thank you. Dude, this is pretty cool. We got widths. We got heights. In order to get areas, I think I should multiply widths times heights. Right, this area is, well, I'm going to show you what it is. It's f of ci, I'm sorry, not ci, little f of mi. What's f of mi? That's my height, thank you very much. That's my height, times my delta x, which is my width. That's what this area is. So let's do it. A 1/2 times a 3. 1.5. 1.5? 1.5. 1/2 times a 3. A 1/2 times a 3.25. 1.625. 1.625? Thank you. A 1/2 times a 4. 2. A 1/2 times this. 2.625. You can use your calculators and help me. Dude, what we got here now is the area of each of the 4 mini rectangles. And what do I want to do with those? I want to add them up. So I add them up. And the answer is 7.75. 7.75. Yep. You guys okay? Wow. All right, now here's what I just did. I mean, I broke it down nice. You guys are nice. You're listening to me. You're nodding. You're understanding this. It's not that hard. It's widths and heights, right? The notation's a little weird, but you get used to it. This is a y value. It's a height. This is a width on the x-axis. You know, I think you. And then when you multiply widths and heights, you get this is an area. See, I'm starting to look at that and see an area of a rectangle right there. It's a height and a width. Anyway, and then I did this for 4 rectangles. So just to get back to this, anyway, you saw me do this without the summation notation, right? I just built a chart and added up 4 damn areas. Just to show you what this 7.75 is it is, well, let me show you what it is. It's the summation of all those little heights, f of mi, times the widths. I mean, it's the summation of these areas, heights times widths, as I goes from 1 to 4. I did this for 4 rectangles, didn't I? Yep. Okay. And, you know, technically I got a little m1 and a little m2 and a little m3 and a little m4. What do I do with the little m1 and the little m2? And what do I do with those? I plug them in the function to get the height. What is my little m1, my little m2, my little m3? It's this little 0 and a 1/2 and a 1, right? These are the things I plugged in the function to get these heights. So, dude, that's what this is. And this is called the lower sum. And it's a lower estimate of the area, right? Because you can see the error, right? There's a hell of a bunch of error right there. There's some error there. There's some error. I mean, the real area is more than this. Do you agree? Okay. Hey, you guys are good. Let's do this again. So now I think I want to do what's called an upper sum. Same problem. I want to do an upper sum. So when I do an upper sum, I use the maximum value on maximum height on each interval. In other words, instead of using inscribed rectangles, now I'm going to use circumscribed rectangles. Circumscribed rectangles. You guys okay? So I'm doing this again. I'm sorry. I'm not sorry, but this is long, involved process. Doing this again, making a little chart. Hey, what's the delta x this time? Same problem.
Same thing.
Same 4 rectangles. Right, okay, so the delta x is the same, the width is the same, there's going to be 4 of them again. What I'm going to get this time is different heights, because I'm going to use capital MI. I'm going to get different heights, because I'm going to do circumscribed rectangles. So here's my heights, and then I'll multiply them together and get area. This time, let's check it out here. I'll tell you what I'll do. I'm just going to erase my little inscribed picture. Let's get rid of these. You might have to draw a new picture. Anyway, I get to erase mine. All right, here I go. For the first rectangle, I want what's called this circumscribed rectangle. See, I want this height. Again, we know that's too much area, don't we? There's some error in there. When I'm done with this, this will be an overestimate. Do you agree? Yeah. But we're going to do it anyway. In order to get the height of the first rectangle, then, do I use this left endpoint?
No.
No, now I use the right endpoint. I plug the half into the function to get that height. So I'm plugging a half into the function. That has nothing to do with the width. It's the half that's that x value. For the next rectangle, what do you plug in to get the height?
1.
You plug in a 1 in order to get that circumscribed height. For the next rectangle, you plug in a 3 halves and you get this height of this rectangle. For the last rectangle, you plug in a 2 and you get this overestimated height. Let's do this. What do we say for the first one? Plug in a half. The next one, plug in a 1. The next one,
3 halves.
Plug in a 3 halves. The next one,
2.
Plug in a 2. That's how I get these heights. Now let's get these heights. Plugging a half into the function, I got over here, if I want to use it right there, it's a 3.25. Plugging a 1 into the function gives me the height of that next rectangle, 4. Plugging 3 halves in the function gives me the height of the next rectangle, 5.25. Plugging 2 into the function gives me the height of that last rectangle. That's pretty high. Plugging a 2 in there, that's a 7. Right, you guys?
Yeah.
I understand this is a little tedious and maybe a little boring, but bear with me. You gotta admit it's fun. Dude, I got heights, I got widths. I can multiply these and get areas. Let's do it. A half times this, I already did that once over there, 1.625. A half times this is a 2. A half times this, that was my 2.625. A half times this is 3.5. These are the areas of my 4 rectangles. I want to do, I want to add these up. And when I add these up, I get something.
9.75.
9.75, thank you. I want to tell you what this is. This is called the upper sum. This is called the upper sum. Yes, ma'am.
Is there any notation written once you add it up in a certain way, or just the 9.75?
So, that's the answer.
Okay.
I want to show you, kind of like I did here. I mean,
Okay.
that here's what it is. Here's what we did. The confusing notation is that I added up all the areas, which were heights, using capital MI this time, heights times widths. I did heights times widths. I did it for 4 rectangles, 1 to 4, and I added them all up. I mean, this math says what I did.
Yeah.
But it's you're new at reading this math, okay? But this says, I keep telling you what it says. It says, add up this quantity. This quantity is widths and heights multiplied together. These are areas of the 4 rectangles that this is me adding up these rectangles, right? But it's the notation that you're not too used to sometimes, but I'm trying to help you read it. That's what I do. Anyway, guess what? Remember, this is an overestimate. So the real area is somewhere between there, right?
Yeah.
All right. Am I happy? Am I satisfied with that?
No.
You want to do a better job? You want to do a better job? You want to have less error? Okay, this is the whole ticket. Can you tell me how to get less error?
Well, you just add them up and take like the divide by 2.
Well, okay. No. I mean, you're not on it. Yeah, right. This was an overestimate. This was an underestimate. And he was suggesting let's average them somehow. That's not a bad idea. I'm saying let's start over, and can we do this better? Can we make him a better underestimate, or can we make him a better overestimate? How can we make these better, more accurate?
Having more rectangles inside? Like,
Do more rectangles.
so have
That's the
smaller,
key.
smaller width.
Do more rectangles. Do more rectangles. It's a pain in the ass, right? I mean, I only did 4 because I knew that's all y'all could handle. But no, but you get the theory? Dude, if you want to make it more accurate and have less error, do more rectangles. And the way you see that, I mean, is if you see this. Watch me. Let's just say I did 8 rectangles. Now, I'm not really going to go do it, but let me draw it for you. If I did 8 rectangles, then I'd have, right? Now, what am I going to do with this one? Like, let's say, so I'm back, because I got this upper sum. So this time I'm going to go here, and I'm going to do this upper sum. And then this next one is this upper sum. So look what I get to erase. I get to erase this much error. Maybe that ain't the best picture. Let's go over here. If I cut this one in half and did another rectangle right in the middle of that, I would circumscribe it right there. This one gets circumscribed right here. So there's still some error there. There's still some error there. But look how much error I just cut off.
It's
I just got rid of all that. That's gone. Are you with me? Circumscribing him here and here, I'm taking off this error. Circumscribing him here and here, I'm taking off this area. Look at that. Look at that. Look at that. Look at that. 8 rectangles, and there's still error. I know there's still error, but we made it better. We made it less error. Well, then hell, let's do 16 rectangles.
Wow.
You with me? Do you understand? Let's do 16 rectangles. Okay, let's do 32 rectangles. That ain't good enough. 64 rectangles. Are you with me? Okay, so you don't want to do 64 rectangles by hand.
Right.
But I bet you could program a computer to do it for you. I mean, computers add shit up real good, you know? Way better than us. But they got to be programmed correctly. They got to be programmed to find the widths. They got to be programmed to find the heights. They got to be told to multiply those widths times those heights and add all that up. Right? Cool. You could do that. It wouldn't even be that much of a, I don't know. You could write a little program. That's not much of a program. You could write a little program maybe to ask a computer to do that. Maybe Excel would do that. So you just learned something. Do more and more and more rectangles, and you zero in on the exact area. I'm going to do something else. I kind of run out of room, so I got to erase something. So we got, what do we got? We got this lower sum here. We got the upper sum here. I got to do another one here. But I'm not going to do 16 or 32 or 64. I'm really not. Okay, don't worry. But in theory, I am. Right? In theory, I am. Mm-hmm. All right, check this out. Check this out. So what we said is there's something called the actual area under the curve. There is a number. There is an actual area. Now what did I do? I found a lower sum. So my lower sum is lower than this. What was my lower sum? It was that 7.75. But watch, I'm going to call it, here's the lower sum. It was I equals 1 to 4 f of little mi times delta x. Do you agree? That was the lower sum? This guy? And that lower sum was a lower estimate of the actual area. Now there was an upper estimate of the actual area. That was the upper sum, and the subtle difference is just this capital MI, because that indicates you're doing the circumscribed, and this is the inscribed rectangles. You still following me? And see, when I start writing this notation, I know you know, but I've been trying to, this is just, we just did this. It's adding up 4 rectangles. It's the area, it's the upper, it's called the upper sum. It's an overestimate of the area. This is an underestimate of the area. The actual area lives there, somewhere in between. Somewhere in between 7.75 and 9.75 for this problem. Okay, so now what did we just say? How do we make him better? Or him better? How do we make both of these better?
Add more rectangles.
More rectangles. Okay, watch. So maybe change it to an 8 or a 16, or right? Okay, watch this. What if I just change it to an n? If I change this to an n, now that could be 2, actually. I mean, an n could be any number. But but I want to do more and more and more rectangles. You ready for this? Here's the thing. Here's the kick. Here's the idea. You want me to do more and more and more rectangles? Here's how you do it. Here's how you do it. You take the limit as n goes to, how many do you want to do? Thank you. I mean, whatever number you say, when you say do 64 rectangles, that's pretty damn good, dude. But will there still be some error?
Yeah.
Yeah. Okay, so do 1,000 rectangles. Shit, that's going to be awesome.
Oh.
But will there still be a little error? Yes, there will. Okay, then do this. Don't do 1,000. Go to infinity.
Yeah.
Do infinite number of rectangles. Do an infinite number of rectangles on this. And I swear to God, you eliminate all error and you get the exact area. You squeeze in, then these things are equal to each other. Then the upper sum, when you put these limits on here, the upper sum becomes better and better and better. In fact, it equals the lower sum. They're not even estimates anymore. Now they are exact area. So that's it. You just got to do an infinite number of rectangles. Piece of cake.
So do you still need the little m and big M?
Hey, did you hear what he said? That was smart, dude. Hey, what did he say? He's kind of right. Here's what they say. Then after you do so many millions of rectangles, this upper sum comes down. You do more millions of rectangles, this lower sum comes up. Then it doesn't matter whether you're using the left or right endpoint. Then they say you can pick any number in there. It doesn't have to be, you can pick any number in the little subinterval. By the way, the little subinterval is tiny as hell now. When you do an infinite number of rectangles, what is their width? Shit, practically nothing, right? But anyway, you're right. Then the big MI and the little MI become insignificant, and they say then you're picking some CI. And so CI is just any X in the subinterval. And you do this, and you do this to n. You're doing n rectangles, but then you're taking the limit as n goes into infinity, and this is exact area, exact area, exact area. No more error. I mean, this game started off as an error problem. Oh shit, there's tons of error. This is an estimate. This is an estimate. It's tons of error. But when you do this, there ain't no error. It's gone. It's exact area.
Are we gonna get it? Shows how to use that.
But doing n rectangles and then taking the limit as n goes to infinity, actually doing this really sucks. I mean, actually doing this is tough. I mean, I don't mind adding up 4 rectangles. I can handle it.
Yeah.
You might have thought it was tedious. I don't mind it. I don't mind doing 4 inscribed, 4 circumscribed. But really doing this, I really kind of can't do. Now, so listen, I don't think I'm asking you to really do this, but I'm excited about you understanding this. And you seem to follow my logic and understand this, maybe.
Mm-hmm.
But actually doing it is something that I'd rather not try to do. The book, they try to do this in 5.2, but it's a very long, cumbersome process, and I'd rather not do it. But I do have something I do want to do. Let me show you, let me do a couple more things. You know what I need though? I need a little 2-minute break. Now hang on, don't leave.